Bismillahirrahmanirrahim. This is another example, and in this example we have to reduce this integral into elliptic integral. In order to do this, we write this expression 2 minus cos x. I write 2 minus cos x, and then we use the half angle formulas of cosine x. You know that cos x is equal to cos square x by 2 minus sin square x by 2, and then I write this sin square into 1 minus cos square x by 2, and finally 2 minus x is equals to 3 minus 2 cos square x by 2, and then I put this 2 minus cos x is equal to this expression into the given integral. We get this expression, and you know that in elliptic integral we need here 1. So we consider 3 is common here, and we get square root 3 outside, and we get this expression. Now you see this integral, and in order to bring this integral into elliptic integral we need here sin x. And remember, whenever you have to convert cosine x into sin x, we need this transformation pi by 2 minus u. This pi by 2 minus u or pi by 2 minus y, all transformation are same, because these transformation transform the cosine into sin x or sin x into cosine x. So because we have angle here x by 2, so we assume x by 2 is equal to pi by 2 minus u, and from this we get dx is equal to minus 2u, and we put this transformation into this expression. We get this expression. Instead of dx we put minus 2 du. We get this expression, and then I write minus 2 outside, and you see here this integral now seems to be elliptic integral. Why elliptic integral? Because in elliptic integral we have here 1, and there we have k square. So what is k? K is square root 2 by 3. So we prove that this given integral is reducible to the elliptic integral form. And now see in example number 7. In example number 7 we have the same integral. This is indefinite integral because we have no lower or upper limit, but now this is definite integral, and the limit is 0 से pi by 2. So we write this integral into 0 to pi by 2, and now we have to prove this integral when limit is 0 to pi by 2 is equal to subtraction of these two elliptic integrals. So to prove this, we know that this integral is equal to this integral. Now we use this transformation. So we put these limits 0 to pi by 2 in these transformation. So what we get when x is equal to 0, we get x is equals to pi by 2, and when x is equals to pi by 2, from this transformation we get u is equal to pi by 4. So I use these lower and upper limit in this transformation. We get these from this expression we get this result, minus 2 over square root 3 by 2, and these lower and this is upper limit. So we get pi by 2 to pi by 4, and same this expression we write here. And now what and then I interchange the limit. Why I interchange the limit? Remember, the lower limit should be less than the upper limit, so I change the inter limits, and then minus sign from changing from lower to upper limit, changing make this minus is positive. So minus is positive, and we, minus is plus, and we get this expression. And what is the problem to make this integral into elliptic integral? Definitely in elliptic integral we need here 0. In definite integral we need here 0. So in order to bring 0 here, we use the property of definite integral here. Remember, one of the property of definite integral is this: integral a to b f of x dx can also be written as 0 to b f of x dx minus 0 to a f of x dx. So if we use this property here, we can write this integral into this form: 0 to b, and what is b? B is pi by 2, and similarly 0 to 4, and what is 0 to pi by 4? we write n pi by 4 is a, so we break this integral from this formula into these two forms. But what is this? This is complete elliptic integral of first kind. So I write f, and what is k? Square root 2 by 3, and what is angle? Pi by 2. Remember, pi by 2 is not necessary, but we sometime we write here, it is depend on our choice, so it is not necessary to write pi by 2 here. Similarly, what is this? This is elliptic integral of first kind, and this is incomplete because angle is pi by 4 and k is square root 2 by 3. So we prove that this given integral is equal to this integral, and the result is proof. Sorry, here we have curly bracket. Here we have curly bracket. Likewise, you see here these square bracket. So we have here actually curly bracket, or you say square bracket. 2 over square root 3 is common from this expression. In next example, we have to find the arc length of this curve y is equal to sin x, and x is, ranges from 0 to pi by 4. In order to calculate arc length in Cartesian coordinate system, we know that the formula of arc length in Cartesian coordinate system is given by this, and in this formula I put x a is 0 and b is pi. So I write here 0 to pi, and then I write square root 1 plus 1 plus, and what is dy over dx? You see y is equal to sin x here. So dy over dx mean derivative of y, and derivative of y mean derivative of sin mean cos x, and square mean square. So we have cos square x. Now remember, we have another property of definite integral which I show you here in this. Whenever now, in order to evaluate this integral, you see this is definite integral from 0 to pi. Let's see this graph. So we have to evaluate the definite integral from 0 to pi. But from the figure it is clear that if we evaluate the integral from 0 to pi by 2 and then we multiply by 2, then we get the same result. Therefore, this integral we can write 2 times 0 to pi by 2. Therefore, and please forget these steps. These are wrong step. So the correct for correct step, see these steps. So the last integral can be written as 2 times 0 to pi by 2 1 plus cos square x dx. And now what is the problem? In order to make this integral into elliptic integral is that we required here minus sine and sine square. So I convert cos square into 1 minus sine square, and we get 2 minus sine square dx. And now what is the problem? To make this integral into elliptic integral, we required here 1. So we consider common 2 here, we get this expression, and now this is complete elliptic integral of second kind. So we can write 2 root 2 e of k, and what is k? Square of 2. So we prove that the arc length of sin x from 0 to 2 pi is equal to 2 root 2 an elliptic integral of second kind, that you see here in this. We prove the result. And this is next example. We have to calculate the arc length of this ellipse, and the parametric form of the ellipse are given by x is equal to a sin phi, y is equal to b sin phi. Remember, a is greater than b and b is greater than 0. So you see the arc length formula in parametric coordinate system is given by, this is the formula of arc length. To use this formula for calculating arc length of ellipse, we have for whole ellipse angle from 0 to 2 pi. So we have to write angle 0 to 2 pi, but you see here in this diagram of the ellipse there is a symmetry. So if you see, instead of calculating whole ellipse, we calculate only the integral from 0 to pi by 2, then we multiply it by 4, we get the same result. And you I hope from the previous example you understand what is the benefit of writing in this way. Last time you see this integral, we write integral 0 to pi by 2, and what is the benefit? The benefit is that pi by 2 makes elliptic integral complete. So we write this arc length formula into complete elliptic integral of second find. So the magic to calculate integral from 0 to pi by 2 is that it will convert the elliptic integral into complete elliptic integral. Therefore, in same here, we if we instead of consider this integral integral 4 times 0 to pi by 2. You see here for calculating arc length, and what is dx over dy? You see here x, and dx over dy is equal to a cos phi. You see here, and what is dy over d phi is minus b sin phi, but due to square we have positive here, so to you see here b square sin square phi. Now we want this integral to convert into elliptic integral, so we convert cos square into sin square by using 1 minus sin square. So a square cos square become a square minus a square sin square phi plus b square sin square phi, and then I consider here sin square phi is common, we get this expression. And because in elliptic integral we required here 1, I consider a square as a common, so we get a here, and here we have 1, and here we get this result. And this whole expression, if we assume that is equals to e, you see here e is equal to a square minus b square over e, then this expression can be written in this form. But what is this? This is complete elliptic integral of second kind. And what is k? K is e, and angle is pi by 2, so we can write in short form as e of e. You see here the arc length of the ellipse is equals to 4a into e of e, and this is very compact equation. This is very beautiful equation. This is the reason that elliptic integral that arise during the calculation of arc length of ellipse, we say these integral are elliptic integral, because they convert the arc length formula of the elliptic integral into very short form, into very compact, into very you say beautiful form. So you see this is a very beautiful expression of expression. I hope you remember many beautiful equations of mathematics or physics. For example, E is equal to mc square, F is equal to ma. All these are very beautiful equations. Similarly, you can if we use elliptic integral, we can write arc length into very short form. Next example, before going to next example, let first I explain this expression. You see this is quadratic equation. So a square, a is the coefficient of x square, or you can say a is quadratic term, b is coefficient of linear term, or we can say b is linear term, and c is constant term. So a is quadratic term, b is linear term, and c is constant term. Sometime in complex integral, you see this is quadratic term and this is constant term. We have only two terms. Number one is quadratic term and number two is constant term. In that case, you have to check the sign. So first of all, you see here this is quadratic term and this is constant term, and these are two factor and both are negative. So there are usually three cases. Number one, negative cases. Number two, positive cases, and number three, negative positive cases. Remember, in negative cases we consider transformation, sign transformation, and in positive transformation we consider tan transformation, and in negative positive or positive negative transformation we can consider secant transformation. So now you see example number 11. Here we have quadratic and constant term, and both terms are and both factor are negative. So we consider here sign transformation. Now the question is that if we consider this transformation from first factor, then we write x is equal to 2 sin theta. But what happens if we consider the second factor? Then we write x is equal to 3 sin theta. So question is that what is the best or natural transformation for this integral to convert into elliptic integral? The answer is that x is equal to 2 sin theta is natural or very easy transformation for this integral. Why? Because the upper limit is 2. Because the upper limit is 2, we will see here in this step the magic of using this first factor as a transformation. If we use the second factor as a transformation, then you get difficult expression for converting elliptic integral to this integral. So because here we have two, so we consider first factor, and from first factor we can write this integral, this transformation as x is equal to 2 sin theta, and then dx is equal to 2 cos d theta, and when x is equal to 0 we get 0 is equal to 2 sin theta, mean theta is equal to 0, and similarly x is equal to 2 mean 2 is equal to 2 sin theta, mean theta is equal to pi by 2. Now we put this transformation into the given integral, we get this expression, and now you see, if we consider 4 here common, we get 4 in bracket 1 minus sin square. 1 minus sin square mean cos square, and this mean we can outside this factor 2 cos theta, and dx is equals to 2 cos d theta, so I write 2 cos d theta, but 2 cos theta is cancelled, and we get this expression. But here you see, here we have 9, so we consider 9 as a common. In order to make this expression into elliptic integral, we get here 1 by 3, and we get this expression. And what is this? Of course, this is complete elliptic integral of first kind. And what is k? K is 2 by 3, and what an angle is pi by 2. An angle is not necessary to write here, so we write is 1 by 3 f of k, or f of 2 by 3. So this is the so we convert the given integral into elliptic integral. This is next example, and you see here again we have here quadratic and constant factor. So remember, whenever you have quadratic and constant factor, so check those factor sign. If negative bring sign transformation, if positive bring tan transformation, and if negative positive then or positive negative bring second transformation. And because this is positive, so we bring here tan theta transformation. But the question is that again here we have two factor. If we write transformation from seeing first factor, then we write x equal to tan theta, and if we write the transformation from watching or studying the second factor, we write the transformation x is equal to square root 2 tan theta. So what is the natural factor for this transformation? So the correct or good transformation is x equal to tan theta, because here upper limit you see here 1. So if you have here 1 and here you also have here 1, so this is a good transformation. Similarly, you see here we have 2, and here we from this transformation we write x equal to 2 theta. So what is happening in the in second in this equation, you see here 2 is cancelled and theta is equal to pi by 2. So if you write the transformation by studying second factor, then your transformation x is equal to 3 sin theta. So what we get, 2 is equal to 3 sin theta, and in this case sin theta is equal to 3 by 2, and in that case you maybe not get standard angle or good angle, but when you use x is equal to 2 sin theta, you get 2 and 2 is cancelled and theta is equal to pi by 2. Similarly here, because upper limit is 1 and from first factor we get 1, that's why x equal to tan theta is natural or good transformation for this question. So x equal to tan theta mean dx is equal to secant square d theta, and x is equal to 0 provide theta is equal to 0, and x is equal to 1 provide theta is equal to pi by 4. Now putting this transformation into the given integral, we get this expression. Remember 1 plus when you put x is equal to tan square, 1 plus tan square means secant square, and secant square when you outside the root we get sec theta, and this secant theta and this secant theta is cancelled, we get here this expression, and we break tan square theta into cos square or into sin square over cos square, and taking the LCM, we get this expression, and then if we consider 1 over cos square outside this root, we get 1 over cos, and 1 over cos, if we consider into numerator, became secant theta, and 1 over cos when we have can be written as secant theta, and I write here, and this secant theta and this secant theta is cancelled, we get this expression. And in order to convert this expression into elliptic integral, I convert cos square into 1 minus sin square. I write sin square into 1 minus cos square, and we get this expression. Now we get here minus sign because we need minus sign in elliptic integral, but the problem is that here we get the cosine square. So now we convert cosine square into sine square by taking the same transformation that we have discussed above many times. So in order to convert cos into sine, we write pi by 2 minus phi transformation, and from this we get d theta is equal to minus d phi, and when theta is equal to 0, phi is equal to pi by 2, and when theta is equal to pi by 4, we get phi is equal to pi by 4, and remember cos pi by 2 minus phi is equal to sin phi. So putting this transformation into this transformation, we get this transformation, and we get this expression, and because the upper limit is lower and lower limit is greater, so we interchange the limit, we get minus sign, and minus minus is plus, so we get this expression. And also we consider 2 is common here, so that we have here 1. Now this is but this is not elliptic integral, because the limit of elliptic integral from 0. So in order to bring this 0, we use the same property of definite integral. You know that a to b f of x dx can be written as 0 to b f of x dx minus 0 to f of x dx. So we can write that integral into this form, 0 to pi by 2 and 0 to pi by 4. But what is this? This is complete elliptic integral of first kind, and this is complete this is incomplete integral of first kind. So we prove that the given this integral is equal. This is next example, and again you see here there are two factor quadratic constant, and because they are positive negative, so we write here this transformation u is equal to secant theta by using this first factor. So u is equal to secant theta mean du is equal to secant theta tan theta d theta, and when u is equal to 1, we secant theta is equal to 1 mean theta is equal to 0, and when u is equal to infinity means secant theta is equal to infinity, and this means theta is equals to pi by 2. So we put this transformation into this given integral, we get this expression that you see here. But remember, secant square minus 1 is tan square, and tan square we can write outside here. You see here tan theta, and further this cos square can be written as 1 over cos square, and after computing LCM we get this expression. This tan theta is cancelled, and 1 over again cos square mean when you outside the integral means secant theta, so I write secant theta, and this secant theta is cancelled, we get this expression. And then I put this cos square into 1 minus sin square, and we get this expression. And now what is the problem? To convert this integral into elliptic integral, we need here 1, so I consider 4 as a common. Here we get 1 by 2, 1 minus 3 by 4 sin square theta. And what is this? This is complete elliptic integral of first kind. And what is k? K is root 3 by 2. And what is angle? Angle is pi by 2. And complete elliptic integral of first kind can also be written as kappa of k. So we can write is half kappa of square root 3 by 2. So you see this is next example, and from seeing this integral, it is clear that it may be elliptic integral of third kind. In order to write this integral into elliptic integral, forget this term, because this term makes this integral into third kind. So only see this integral, this expression. And what is this expression? This is quadratic constant expression. So because this is quadratic constant expression and factors are one positive, one negative, so we use second transformation here. So let u is equal to second transformation second theta, du is equal to second theta tan theta, and when u is equal to 1, second theta is equal, provide theta is equal to 0, and when u is equal to infinity, theta is equal to pi by 2. This is the same transformation that we used in last example number 12. So we put this transformation into the given expression, we get this expression, and then you see this is second square minus 1, and second square minus 1 mean 10 square, and when you put tan theta outside this root, that tan theta and this tan theta is cancelled, we get this expression, and here we write second square 1 over cos square. Similarly here we write this second is 1 over cos square, we get this expression. So and then we cancel this 1 over cos square. When we bring it into outside the root, we get 1 over cos, and that means second theta, and that second theta and this second theta is cancelled, and this is 1 over cos square means second square, the means 1 over cos square, and that cos square we can write here. So we write here cos square this. So we have this expression. Now we write the numerator into this form, 3 plus cos square minus 3 theta. In fact, we just add and subtract 3 and minus 3, and then we break the integral. From first we break this expression, this LCM, we break this expression is cancelled, we get this expression, and from this second integral we get this expression. So we get these two expression, and then we convert this cos square into sin square by using cos theta is equal cos square theta is equal to 1 minus sin square theta. We get this expression. Similarly here we put cos square is equal to 1 minus sin square, we get this expression, and then we consider 4 common here. Similarly we get we consider 4 common here, we get this expression. And what is this? This is complete elliptic integral of first kind that we denoted by kappa of k. And what is k? K is root 3 over 2. And what is this? This is complete elliptic integral of third kind. And what is k? K is root 3 by 2. What is n? N is minus 1 by 4. And because this is complete, so no need to write the angle pi by 2. So this is our answer, or we convert this integral into these elliptic integral. In the next example we have to just show that we can convert this such type of integral into elliptic integral. Can we convert such type of elliptic integral into elliptic integral? So to convert this integral into elliptic integral, we first put this transformation. Let x is equal to y plus alpha. This means, and alpha is constant, and alpha we determine by using geometry of the problem or initial or boundary value of the problem or any some other constant. So to determine the value of the alpha is depend on us. From this we get dx is equal to dy, and we get this expression. So I write again this expression and put x is equal to y alpha. We get this expression that you see here. Now in order to determine the alpha, what we do here, we suppose these, you see these are last term, these are last constant term in first factor, and this is the last constant term in the second factor. In order to determine the value of alpha, we assume that the both factor should be equal. So I equate these two constant term into expression. We get this term, and from this expression alpha square is cancelled, and we get alpha is equal to 1. So I put alpha is equal to 1 in this expression, we get this expression. Now what is the difference between this equation and first one? You see here in first one both factor are quadratic linear constant, and second one is also quadratic linear and constant, and but we know only the method to solving quadratic constant term. So our first aim is to convert this quadratic linear constant term into only quadratic and constant term, so that by this previous method that either positive positive or negative positive or negative negative, we can solve this expression. So our aim is to convert this expression into quadratic constant term instead of quadratic linear or constant term. And now you see from this expression we convert our first factor into quadratic constant, but the second one is remain on quadratic linear and constant. Now our aim is to convert this second factor into quadratic constant term. To convert this factor into quadratic constant term, we assume that y is equal to beta u, and again remember we can determine beta with the same geometry of the problem or initial or boundary value of the problem or by some constants of the expression. So let y is equal to beta u, then dy is equal to beta du, and put this very simple transformation into this expression. We get this expression, and now in order to determine the value of beta, we assume that the coefficient of quadratic term and constant term should be equal. I repeat, in order to determine the value of the beta, we assume that the coefficient of u square or quadratic term is equal to the constant term, and what is the coefficient of u square in both expression is beta square, and what is the constant term in both expression is 9. So we equate beta square is equal to 9, and this means beta is equal to 3. So just put beta is equal to 3 in this expression, we get this expression. You may say what is the difference in this expression and this expression. Yes, there is a difference. The difference is that here you see coefficient is 1, 3 and 9, but here you see coefficient 1, 1, 1, and that much is easy from this expression because the coefficient of this expression is 139. So here we have 1 1 expression, and from the advanced calculus or advanced integral, we know that whenever we have such type of expression and to convert such type of quadratic linear and constant term into quadratic constant, we bring this transformation. U is equal to 1 plus t over 1 minus t, and this means du is equal to this expression, and just put this simple expression into this expression, we get this expression. And what is it? This is quadratic constant and this is quadratic constant, and both are positive. And remember, when both are positive, we use this transformation. Tan theta transformation. So in this example, our objective is just to write the expression in such a form that can be later on written as a elliptic integral. So we convert this quadratic linear constant term at the end after 3 transformation into quadratic constant term. And now we know that whenever we have quadratic constant term, using t is equal to tan theta transformation, we can always convert such type of integral into elliptic integral. So in this example, we have to just give an idea that the given when we have integral of quadratic, linear and constant term, then how we convert such type of integral into elliptic integral. Then so what we have done here, we just use 3 transformation and we get quadratic and constant factor. And we know that whenever we have quadratic and constant term and terms are positive, then we use t is equal to tan theta, bring this integral into always bring this integral into elliptic integral. So this is the idea that we have proved in this example. Please cancel this solution because this solution is not good. Why this is not good? The solution is not good here. You see here, this seems to be elliptic integral. I say this seems to be elliptic integral, but it's not elliptic integral of first kind. Why? Because k is root 3 here, and k is root 3 is greater than 1, and this means k does not belongs to between 0 to 1. So in order to bring this integral into elliptic integral, we must bring this transformation that I give you here. Hint is, put u is equal to square root 3 sin x. Put u is equal to square root sin x, and then solve this example as in the previous example. And this is the end of this chapter. So this elliptic integral is complete here, and I stop this chapter here. In the next chapter, lecture number 12, we will provide some lecture of some exercises of this chapter. So let's start next chapter that we call improper integral. So next chapter is improper integral. Improper integral, remember, like elliptic integral, there are like three type of elliptic integral. Similarly, we have two type of elliptic integral. The first one is called improper integral of first kind, and second one is called improper integral of the second kind. Why they are called improper integral? The improper integral is called because the infinity is involved in this integral. So if infinity is involved either in lower, upper, or lower and upper in both limits, then this is called improper integral of first kind. And you know that in integral, this f of x is called integrand. So if this f of x is infinity either on lower or upper or in between number c, then this is called improper integral of second kind. Let's see this chart here. Use here we this is the improper integral of these are the example of improper integral of first type, and these are the improper integral of second kind. So this is the improper integral of first kind and first type. This is improper integral of first kind, second type. This is improper integral of first kind, third type. So when you only your lower limit is infinity, then this is called first kind, first type. When your only upper limit is infinity, then this is called first kind, second type. And when your both limits are infinity, then this is called first kind, third type. Similarly, when your function f of x is infinity on lower limit, for example, f of x is equal to 1 over x minus a. You see, when we put x is equals to a here, this function became infinity. So this is called improper integral of second kind and first type. And when your function is infinity on the upper limit, on the b, then such type of integral is called improper integral of second kind and second type. And when your function f of x is infinity between the number a and b, for example c, you see here f of x is equal to 1 over x minus c, then this is called improper integral of second kind and third type. So we have these type of two improper integral, and the question is that how we solve these improper integrals. So first let we discuss the improper integral of first kind and how to solve and how we define or how we compute the improper integral of first kind. Let's see the first improper integral of first kind and first type. And in first type, you know that the lower limit is infinity. So the scientists defined this first type can be written as limit t tends to infinity and t to be f of x dx. And what we have to do, just compute this integral, and at the end put t is equal to infinity. You may ask, what is the difference between the left hand side and right hand side? There is a big difference between left hand side and right hand side. Remember, in left hand side you exactly equal on infinity. Remember, on left hand side you exactly on equal to infinity, but in right hand side you never be equal to infinity because you write t tends to infinity. And remember, in mathematics x tends to a mean x not equal to a. Remember, in mathematics x tends to a mean x never be equal to a. You always move towards a but never be equal to a. So in mathematics, whenever we say x moves to a or towards to a, means x never equal to a. Similarly, here when we write t is equal to t tends to infinity, means t never equal to infinity. So t never equal to infinity, then this means left hand side is not equal to right hand side. Then you may ask why they are equal. The answer is that the scientist is defined in this way. There is no other way to define in this way. So scientists define whenever you have to compute a first kind and first type of integral, just write t tends to infinity and t to be f of x dx and compute this integral, and at the end put t is equal to infinity. Similarly, first kind and second type is defined as a to infinity f of x dx as limit t tends to infinity a to t f of x dx, and compute this integral, and at the end put t is equal to infinity. Similarly, so first kind and third type can be evaluated in two ways. First way is simple is that, and we in whole chapter follow this first method. Write t tends to infinity and write here minus t to t f of x dx, and at the end put t is equal to infinity. We get the answer of third type. And the second way is that of solving third type is that bring this integral minus infinity to infinity into minus infinity to c and c to infinity. C is any number between minus infinity to infinity. And what is this first integral? This is first kind and first type. Why? Because the lower limit is infinity. And what is this? This is first kind and second type because the upper limit is infinity, and we can solve it by first type, and we can solve this integral by second type by writing t tends to minus infinity and t to c f of x dx, and we write this second integral as limit t tends to infinity c to t f of x dx. So this is first type and this is second type. Evaluate both integral, and if both are convergent, then this third type is convergent. If any one of these integral are divergent, then this third type of integral is also divergent. Improper. So these are the ways of computing improper integral of first kind. Now before computing improper integral of second kind, I recall you the some fact about real analysis of NED first year. You know that in real line minus infinity to infinity for any number c that is between a and b, we can move in two ways, either from left hand side or right hand side. So if we move towards c from left hand side, we write c negative. C negative just mean we move towards c from left hand side, but we never be equal to c. Similarly, c positive mean we move towards c from right hand side, but we never be equal to positive. C. Similarly, if you see this improper integral a to b f of x dx, our lower limit a means we equal to a or greater than a, and upper limit is b means we always equals to b or less than b. So you see here we have a. This means we only move towards a from right hand side, because in this integral a we always equals to a or less than a, but never be always a equal to a or greater than a, but never be less than to a. So we move only a towards a positive. Similarly, from b we can move only from left hand side, not from right hand side, because we never be greater than a. So integral from a to b mean we always equal or less than b, and less than b mean we always moves towards b from left hand side, that we denoted by b minus. So remember, whenever you have lower limit, you can write a positive, because on a we can move only from right hand side, and whenever you have upper limit b, we can write b negative, because we move towards b only from left hand side. But the number c that is between a and b, we can move c either from right hand side or left hand side, and in that or in those cases we can write either c positive or c negative, etc. We will continue this in the next lecture. Jazakallah khair.